also get through some content to it too. All right, so I just want to get you back in the mode for a moment. You did a lot of that reading last night, especially about the history, light, and a lot of the quantum mechanical model. Today, I just want to kind of touch base about atomic structure, making sure you remember how to determine isotopes, electrons, protons, neutrons, electrons, ions, electron configurations, and so forth. Okay, so I didn't copy in the back, so like for lab stuff you can cut out just fine. You can also write on the back of that if you want to keep everything in the packet. Do whatever you need to. Okay, so have periodic table out. Have calculator out. We're really just going to hit examples to make sure you can apply this. Who remembers kind of a good amount of this from honors math? At least that you've been exposed to it. Like you have been exposed to every bit of this, and it's not like something I need to teach you the nooks and crannies of. Like, oh, there's a special approach to writing electron configurations. It's one and done. It's like you know it and you're moving on. So that's why we're just going to hit examples mainly right now. Okay. So I gave you the reading so that it was kind of a little bit more condensed and it was accessible to you now. We're going to do a quick atomic or average atomic mass calculation. It's question 7, 8, and 9 on that very first section that you just read. All right, so given the fact that you have boron, what is boron's atomic mass on the periodic table? Everybody has a periodic table nearby, even if you're looking at honors math. Say again? 10.81, right? Okay, so that's the average. Is there an actual atom of boron that weighs that? No, it's an average of all the versions of boron that exist in the world. So the two versions, or the two isotopes of boron, or boron 10 and boron 11, you can see that I don't give you exact masses, it's just boron 10, boron 11, but you can see who's most prevalent. Who's most prevalent? Boron 11, it's 88.22%, this is like 20%. So what you can see, one, is that the average atomic mass is a weighted average, just like your GPA is a weighted average, right? So that's why, can somebody explain why this mass, or why it's important that this one's more abundant?
Because it tells you the average atomic mass is going more towards 11.
Right, so that's why it's 10.81, because it's leaning more towards the 11 one than the 10 one. So there's only two steps. Take one mass, multiply by its percent as a decimal. So take that decimal, or take that percent, back it up 2 decimal places, because that's you dividing by 100. So that's 0.1978. And then take the other isotope, boron 11, multiply by its percentage as a decimal, also known as relative abundance. So relative abundance is just another way to say percent abundance. So when you multiply these values, somebody tell me on the first one. 1.97 what? 8. Second one? 8.82. And so after this, what do? Add. Don't do anything at the end. No division, nothing crazy. You've already accounted for that division because you've started up front with percentages. So add that, what will be it?
10.80.
Yay, I was hoping it was really close. So what's AMU stand for? Atomic mass units. So this was two isotope examples, so we only had 2 isotopes we were dealing with. The second one here has 4 isotopes. It would just be a little longer, right? 4 isotopes, 4 percentages, add them up at the end. I'm not doing that question. Is that okay? Okay. Some of these are just quick reminders, okay? This is question 8. So you have element X, 45, 46, 48. If the average atomic mass, so it doesn't say average, but if the average atomic mass of the element is 45.23, which isotope is most common? Isotope 45, right? Why? Good. So the average is skewed towards a mass of 45. So therefore, the most abundant one is going to be the one that weighs mass of 45. So far, so good? So with some of these, like this is the only day I'm mentioning isotopes. Okay, so just because I'm not spending a lot of time on it doesn't mean it's not important. So do make sure that you're aware that you're still responsible for this information. Okay, so copper 65 versus copper 63. What's the difference first? Neutron count, right? Mass is going to be, what composes mass? So mass is equal to protons plus neutrons. So what's the proton count on copper? 29. So they both contain 29 protons. Copper 63 contains 29 protons and what? I believe you, okay. And then the other one, 29 protons and... So essentially these are isotopes to each other, different by just the mass of 2 neutrons. Do they have the same chemical and physical properties? Yes, they are all copper. One of them might be more stable than the other, meaning maybe it's more radioactive than the other, which has a little bit to do with its chemical property because that means it's a little bit more reactive in terms of its nucleus breaking down. But they're all, what are some properties of this copper, of metal? Malleable, ductile, conductive to electricity, and you put a pot in the stove or in the oven, heat, right? Thermal energy and electrical energy. It's probably very reactive with, actually copper is pretty inert, but some metals are very reactive with different types of different forms of gases. Okay, so that's atomic structure, right? The next section talks about how we lead into making atomic structure. The most important subatomic particle is the electron. The electron causes all kinds of cool things, like light energy to be revealed when electrons are transitioning between energy levels. So we have this relationship aspect that we're going to speak to, but I'm going to hold off first because I'm going to finish atomic structure. Okay, so come right back. Oh dang, I do have to tell you this first. All right, so Coulomb's law, we actually have applied it many, many times. It's just we've never really put a face with a name. So what you should know, because now we're dealing with the atom, we're dealing with protons and electrons, there are some things that are going to be attractive and some things that are repulsive. So what we have this rule, we have Coulomb's law, we never actually calculate F. We never do. We look at relationships. It's all qualitative more so. So read first, write down what you need to, and then I'll explain via the equation. Timer on for myself. So basically, Coulomb's law runs every single explanation or justification we have to make. You won't always say, Coulomb's law says blank, but you'll actually be mentioning something related to it. So what this is going to refer to with subatomic particles is if you have a nucleus, and normally we know that this is not actually what the atom looks like, it's just the kind of the version of the Bohr model we like to draw. If the nucleus is here, and you have an electron here on energy level 2, and then you have another electron on energy level 4, you should be able to tell me who is more attracted to the nucleus. Who has a greater force of attraction to the nucleus? Number 2, right? Energy level 2 versus energy level 4. So energy level 2, electron in here, is actually lower in energy because it's stabilized by this attraction to its own nucleus. The energy, or the electron in energy level 4, has more energy because it's less attracted to its nucleus, so it's crazier. It has more energy it can bounce around with. So we base it off of distance, really. So you can have protons attracted to electrons, and we have the F and the K value, but we actually literally never calculate it. I think maybe I calculated in college like twice, so it's all like qualitative. So if we have a proton and an electron, the attraction is greater, so the force of attraction is greater under what kind of distance? Low distance, right? And it's d squared, it's distance squared, but in reference to this, we're looking at a lower distance. So the force of attraction is greater in that scenario. The force of attraction is proton, electron, is smaller under a situation where you have a large distance, or a large value for d squared. So that makes sense, right, related to the direct and indirect proportionality. Another thing we could consider, though, outside of attraction is repulsion. What types of things repel each other? Like charges, right? So, for example, if I have an electron here and an electron here, they're going to spread apart. Why? So if I put an electron here and here, are they relatively close or far away? They're relatively close the way I've drawn it here. So their force of repulsion is high, okay? So that's like the low distance, that their force of repulsion is high. So they tend to spread themselves out to limit repulsion, because repulsion makes your atom very unstable. That's not a healthy environment to live in, so therefore it fixes itself. So we can also relate this to force of repulsion. That will be very important when we start to talk about orbitals, where electrons live in the orbitals, and why they exist in one orbital but not maybe both together, and so forth. Basically, electron configurations. Can I go past this? Okay. I'm going to make sure that you know atomic theory stuff later. It's just reading Dalton's atomic model. Okay. Same thing with the theory behind it with multiple proportions. Here is the 250 years of research on the atomic model. It was a blob. What is this model called? Plum pudding model. So J.J. Thomson thought there were negative charges based on his cathode ray tube experiment when he held up the magnet and it deflected, or it attracted based on whichever side of the magnet he was holding up. So he came to this conclusion. Rutherford was like, whoa, shoot some alpha particles at it. Doesn't go straight through. What? There's a nucleus, it's hard and dense. Alpha particle bounced off. That's an alpha particle. Do you remember that? Nuclear chemistry, barely. That's an alpha particle. So it shot off. So he was like, okay, stuff's got to be centralized. The rest of the area is going to be just diffuse. Bohr came up with the energy level diagrams, kind of like that. But really, his atom is, or his model is only true for hydrogen. So Schrodinger, Einstein, Heisenberg, Planck, etc., piggybacked off of Bohr's research and took this orbit. Bohr called these orbits, and they said, we're going to take these orbits and make them electron clouds, and we're going to call them orbitals. Big change, right? They couldn't choose another word, but they went from orbits to orbitals, and this electron cloud model, which is now termed the quantum mechanical model, which is our most current version of what we think the atom looks like. History. Okay. Subatomics, Z number, if I ever say Z number, it means atomic number, also known as the number of protons. If you have a neutral atom, let's say lithium, how many protons does it have? 3. If it's neutral, how many electrons does it have? 3, right? If you make an ion, what particle are you changing? Electrons. Why do we not touch the protons? The identity, right? And plus, it's hard to get to because it's inside the nucleus, right? Electrons are much easier to gain or lose because they're on the outside of the area. neutrons, I say sometimes change. It's literally just because, like, when we have isotopes, you can change the mass, which is because you're changing neutrons. I just like this fun fact about the neutrons because we know that in the nucleus we have a bunch of protons, right? What do protons and protons and protons do together? Repel, right? So they can't be that repulsive inside the nucleus because it's supposed to be a stable environment. So what the neutrons are doing, that's a neutron, they're kind of buffering the region between the protons so they don't get so repulsive and unstable. So they're kind of like peacekeepers, or they're a strong force that keeps the nucleus together because of the limitation of repulsion. And then electrons will equal protons if it's neutral. What's the name of a ion that loses electrons? Cation. And then gaining electrons? Anion. Because cats are positive. I said that in honors chem, nobody got it. I was like, you guys are a joke. Okay. All right, ready? Moving on. Cats are positive. Okay. So because we identify isotopes in two different ways, just want to make sure you're comfortable with both. This is the A to Z notation. This is the mass notation. So write the A to Z notation for copper 63 with a 2+ charge. Copper 63 with a 2+ charge. Right. CJ symbol. Copper 63, 2+ charge. Listen to like what I'm saying right now. Give me the symbol. Fine, just the symbol. I'm not doing this part down here yet. Cu, 2+. Drew, give me the A number. No, go back. What did you just say? What did you just say? Sorry, I said 63, but I'll go with that, okay? So copper 63 is what I said. So this A number is the mass number. It's the mass of that isotope. It could be really close to what's in the periodic table, or it could be far away, because remember, isotopes come in many forms. Okay, so 63, copper 2, and then everybody, what's here? 29. No math required. It's really exactly what I say, plus the reading from the periodic table, because you have to find the atomic number. If I had carbon 12, just carbon 12, it's carbon-12. That means that's the atomic mass, and then everything else you can pull from the periodic table, right? Atomic number and so forth. All right, try to fill out this chart. No, I didn't print it. I don't think I printed it. You see how much I printed. I printed a lot of resources too. Yes. Just this stuff. I don't want to see my copy count for anything. I copy everything for everything. I copy something. All right, we'll process some together, okay? Chase and Miriam, can you guys give me the nitrogens row? 7, because that's the atomic number. So what did you pull information about? For this 7 over here, what did you pull? No, every single atom in the world is an isotope. Keep going. Where'd you pull information? Like, you had to get that information from someplace. Chase? What's the atomic mass? Okay, so you had to pull from the periodic table, because in places I don't give you a mass, you have to pull from the periodic table. But if it was like 14.5, there are no halvesies on neutrons, right? So you have to round it to the closest one. Well, this one was easy. It was 14, like on the dot, right? So it was actually 14 and 7, and so if that helps you to fill it out to kind of isolate what you're talking about, that's good. 7 protons, 7 neutrons, because 14 minus 7 is 7. Everybody, electrons? Good, good, you went up. Okay, you're gaining 3 electrons. That's going to get a negative charge, not 4. Okay. Chromium 51, everybody, proton. And that's the atomic number. How do you get neutrons? 51 minus 24, which is, and electrons. Good, because it's the same as the protons, because it is a neutral isotope or neutral atom. Potassium, 19 is its 19 is its, how that happened. Proton count, keep going. Give me electrons next. Good, you went down because it has a top. Well, tell me what that means. Good, it lost 1 electron. Positive charge means you lost 1 electron. Do not change the protons. And then 20, because 39 minus 19 is 20. Yay, atomic structure. Good? Okay. You might remember this mass spectra, where we have this device where you throw like a sample of gaseous atoms through. And so if I had oxygen 16 and oxygen 18 in that mixture, and it was put through this spectra, or this device called a mass spectra, which of the atoms or isotopes would be deflected more through this magnetic field?
16.
Say that question, Lee.
16.
16 with confidence. Why?
Because it's lighter.
Because it's lighter. Lighter things can be deflected more. So this path of 16 would kind of go way up here. It would be detected on the detector higher up. So it's going to count how many times the atomic number or the isotope 16 hits. So because it's lighter, it's deflected more. Okay, and then the heavier one, 18, is going to go through the magnetic field, and then it's kind of heavy, so it's not deflected quite as much, so it's going to hit the detector down here. It's going to count how many times it's being detected, and it's going to come out with a graph. Okay, so the graphs that we've been exposed to, this is our midterm even, were these little intensity versus mass graphs. Remember those? Okay. Now, of course, I drew a bunch of lines, but how many would this one create? 2, right? Because there are only 2 isotopes. One that weighs 16 and one that weighs 18. And I drew this correctly because what is the average atomic mass of oxygen? 16. So you're going to have a lot more, probably like 99% of the 16 one hitting the deflector. It's going to count that based on the hitting of the deflector or the detector, and then very little of the oxygen 18 just because it's not as abundant in the world. Okay, so that's our mass spectrographs. Okay, and that's just information regarding atomic structure because it's dealing with masses. That's really the only thing. Okay. Oh, darn, I'm out of time. Okay, so I'll talk about electron configurations tomorrow. One thing I want you to do, because we're not going to get that done. Okay, so I'm going to show you this now. I just uploaded the 100-slide PDF of all these notes, okay, under Unit 10. You see this? You're not going to go through 100 slides. You're going to go through a couple, okay? So when you go there, I just closed it. Hold on. We've gotten through here, right? Okay. I just want you to take some notes on your own so tomorrow I can do the examples before our lab, okay? So I want you to go through, I'll tell you what page, because using the page numbers down here, right? Like we're on page 3. So finish page 3 and 3 through 6. Let's do that. Finish page 3, 4, 5, 6. Okay? Now, of course, you don't have to write down everything, but it would be a good idea to set yourself up for success. So leave a little space so you can do some examples as I do in class. Alrighty? Good job, guys. Thank you. You got 2 minutes to refresh your brain before second period. If I need to talk to somebody, flash me in MSI's like right here. So line up. Show me where you go, okay?